For over 60 years, every iconic image and word from space, Neil Armstrong's first steps, the James Webb's cosmic vistas, has reached us via radio waves. But radio is maxed out. Imagine streaming 4K video on dial-up. That's NASA's problem as we send more advanced missions deeper into space. The data we want to send is overwhelming our old systems. Now, NASA is on the verge of a revolution, swapping radio for focused beams of light, lasers. This leap is like jumping from smoke signals to fiber optic internet, unlocking faster, richer science from the farthest reaches. Today, we'll break down why radio can't keep up, and how NASA's new laser tech will transform space communication. Let's dive in. Space exploration is pushing the boundaries of what's technologically possible. But there's a bottleneck. Here's why NASA needs an upgrade, fast. The current communication infrastructure is struggling to keep up with the demands of modern missions. First, bandwidth radio waves are a narrow highway, fine for the 60s, when missions were simpler and data was scarce. Back then, transmitting a few images from the moon was a monumental achievement. But now we're trying to send fleets of data trucks, a massive influx of information that the old system simply can't handle efficiently. HD video, offering unprecedented views of distant worlds, complex science, generating vast datasets that require detailed analysis, software updates, essential for keeping spacecraft running smoothly and adapting to new challenges. Down a two-lane road. It's like trying to stream a 4K movie over dial-up internet. Radio's low frequency means limited data per second. The amount of information we can squeeze into each radio wave is fundamentally restricted. Mars rovers collect gigabytes, capturing stunning images and crucial scientific measurements, but it trickles back to Earth over days or weeks. This delay hinders real-time analysis and decision-making. Second, signal loss. Radio waves spread out and weaken over millions of miles, becoming fainter and more difficult to detect as they travel across the vast distances of space. Like a whisper in a stadium, the signal gets lost in the noise. We need giant, expensive antennas to catch them, massive dishes that can focus the faint signals from the depths of space. Third, latency. Even at light speed, signals from Mars take 20 minutes one way. This round-trip delay can be almost 3/4 of an hour. No real-time control, just batches of commands and long waits. Imagine trying to drive a car on Mars with a 40-minute delay. Fourth, crowding Earth's radio spectrum is packed with cell phones, Wi-Fi, satellites, and countless other devices vying for bandwidth. Deep space uses protected bands, but near Earth, it's chaos. Interference and congestion are constant challenges. Added up, slow, weak, delayed, and crowded. It's a recipe for frustration and inefficiency. Radio is holding us back. It's time to move beyond the limitations of this legacy technology. To stream live 4K from Europa or run a moon base, enabling immersive experiences and real-time operations, we need a new approach. A paradigm shift in space communication is essential. Enter lasers, a technology that promises to shatter these limits, offering vastly increased bandwidth and reduced signal loss, and build a cosmic information superhighway. This new infrastructure will revolutionize how we explore and interact with the universe. Let's see how. Let's delve into the science and engineering behind this exciting new frontier. Laser communication is a game changer. Instead of broadcasting in all directions, lasers send data in a tight, focused beam, thousands of times more bandwidth than radio. Imagine upgrading from a country road to a superhighway, 10 to 100 times more data, sent faster than ever. High-def Mars video in days, not weeks. Scientists get results faster, astronauts get better calls home, and we get a front-row seat to space. Lasers are also more efficient and secure. The focused beam stays strong over distance and is tough to intercept. Smaller, cheaper ground stations can receive the signal. The catch? Precision. Hitting a tiny receiver on Earth from millions of miles away is like hitting a dime from a mile away, while both are moving. Weather is another challenge. Clouds block lasers, so NASA's building multiple ground stations worldwide. Despite these hurdles, the payoff is huge. NASA's already testing and refining this tech. The future of space communication is here, and it's made of light. Before we build a laser internet for the solar system, we need to prove it works. That's where NASA's Laser Communications Relay Demonstration, LCRD, comes in. Orbiting 22,000 miles above Earth, LCRD relays laser data between ground stations in California and Hawaii. Its telescopes, mounted on ultra-precise gimbals, lock onto ground stations and keep the beam steady, even as the satellite moves. LCRD tests everything: atmospheric distortion, rapid switching between stations, and maximum data rates. Adaptive optics, mirrors that flex hundreds of times per second, keep the signal clear through shimmering air. LCRD is also a relay. Future spacecraft can send data to a satellite like LCRD, which finds a clear path to Earth. This makes the network flexible and robust, even for missions on the far side of the Moon. Every experiment builds the rulebook for laser comms, paving the way for deep space missions. LCRD is the crucial stepping stone, next taking lasers beyond Earth's orbit. LCRD proved lasers work near Earth, demonstrating their potential for high-speed communication in our planet's vicinity. This was a crucial first step, validating the technology and paving the way for even more ambitious applications. Now, DSOC, the Deep Space Optical Communications Experiment, takes the leap to deep space, venturing far beyond our familiar surroundings. This groundbreaking experiment aims to push the boundaries of laser communication, exploring its capabilities across vast cosmic distances. Hitching a ride on the Sefgi spacecraft as it embarks on its journey to explore a unique metal-rich asteroid. This provides DSOC with the perfect opportunity to test its technology in the challenging environment of deep space. DSOC aims to beam high-bandwidth data from the asteroid belt back to Earth, showcasing the potential for transmitting large amounts of information across interplanetary distances. This could revolutionize how we receive data from future space missions. The challenge: hitting a tiny target on Earth, requiring incredible accuracy and sophisticated tracking systems. It's like trying to shine a laser pointer on a specific grain of sand from miles away. From hundreds of millions of miles away, where the vastness of space presents significant obstacles for maintaining a stable and reliable connection. The sheer distance introduces delays and signal degradation that must be overcome, with a laser that travels for 20 minutes, highlighting the immense distances involved and the need for precise timing and synchronization. The light we see today left its source 20 minutes ago. DSOC uses an uplink beacon from Earth to lock on, providing a reference point for the spacecraft's laser to target. This beacon acts as a guide, ensuring that the signal reaches its intended destination, then points its own laser with mind-blowing precision, all autonomously, without direct human intervention. This level of automation is crucial for deep space missions, where real-time control is impossible due to communication delays. In 2023, DSOC sent its first test signal, marking a major milestone in the development of deep space laser communication. This successful transmission demonstrated the feasibility of the technology and its potential for future applications. And even a high-def cat video from 10 million miles away, a light-hearted demonstration of the system's capabilities. The video, featuring Taters the cat, captured the public's imagination and highlighted the potential for transmitting rich media content from deep space, a landmark for deep space data, proving that high-bandwidth communication is possible even across vast cosmic distances. This achievement opens up new possibilities for scientific discovery and exploration. As Sefgi travels farther, venturing deeper into the solar system, the challenges for DSOC will only increase. DSOC will push for gigabit per second speeds, a data rate comparable to what we experience with modern terrestrial networks. Fiber internet, but from deep space, offering a dramatic improvement over traditional radio communication methods. This tech could let Mars rovers send daily 4K video, providing scientists with unprecedented access to high-resolution imagery of the Martian surface, or map planets in record time, accelerating our understanding of the solar system and beyond. The ability to quickly process and transmit large datasets would revolutionize planetary science. DSOC is the proof of concept for making lasers the main way we talk to distant spacecraft, replacing the limitations of radio waves with the speed and efficiency of light. It's turning the dream of a high-speed interplanetary network, connecting spacecraft and enabling seamless communication across the solar system, into reality. A future where data flows freely between Earth and our robotic explorers, unlocking new possibilities for scientific discovery. The future of deep space communication is here, and it's blazing fast, promising to transform how we explore and understand the universe. Next up, the quantum leap, exploring even more advanced technologies that could revolutionize space communication in the decades to come. Lasers are fast, but what about unbreakable security? Enter quantum communication, the next frontier. At its core is quantum entanglement, two photons linked so that measuring one instantly reveals the other's state, no matter the distance. This doesn't send info faster than light, but it does create a perfectly secure channel. NASA could send entangled photons to Mars. Any eavesdropping would instantly be detected, as the quantum state would be disturbed. It's security guaranteed by the laws of physics, ideal for protecting critical mission data. NASA's just starting, with small-scale tests on the ISS and in labs, working to keep these delicate quantum states stable over long distances. The potential is huge. Quantum comms could one day make space data as secure as nature allows. For now, lasers are the big leap, but quantum is the step after that. The future of space communication isn't just fast, it's fundamentally secure. The groundwork is being laid right now. Fast lasers are only half the story when it comes to building a reliable interplanetary network. While they provide the high-speed data links we need, they don't solve all the challenges of communicating across vast distances. The internet we use on Earth, with its robust infrastructure and constant connectivity, simply can't handle the unique challenges of space, including significant delays and frequent disruptions caused by solar flares and other cosmic events. These factors can easily knock out communication links. Enter Delay/Disruption-Tolerant Networking, DTN. This technology is specifically designed to overcome these hurdles. Think of it like a cosmic postal service, designed to get your message through, no matter the obstacles. Instead of needing a live, continuous connection, which is often impossible in space, each spacecraft or satellite acts as a node, storing data temporarily and intelligently forwards it along the network when the next communication link becomes available. It's all about store and forward. For example, a Mars rover can send its collected data to an orbiting satellite, which then holds onto that information until it's in a position to pass it along to a relay satellite closer to Earth, which in turn waits for a clear, unobstructed shot to transmit the data back to Earth. The data hops efficiently from node to node across the vast expanse of space, gracefully surviving hours, or even days, of communication blackout periods due to planetary shadows or solar interference. DTN is incredibly robust. There's no need to panic if a connection suddenly drops. The data simply waits safely and patiently for the next available opportunity to be transmitted. NASA has already rigorously tested DTN on the International Space Station and on various experimental missions designed to push the boundaries of space communication. And now, it's ready for prime-time deployment across a range of future missions. As we begin to establish permanent networks around the Moon, supporting lunar habitats and scientific outposts, and as we expand our presence on Mars, building a Martian internet for future explorers, DTN will serve as the crucial backbone, providing the reliable connectivity we need. It will be instrumental in ensuring that data flows reliably and efficiently across the entire solar system. Combined with the speed and bandwidth of laser communications, DTN is the intelligent software and robust hardware foundation upon which the entire interplanetary internet will be built. Soon, data will move seamlessly across the vastness of space, with the same ease and reliability that we currently experience here on Earth. The future of space networking is resilient, adaptable, smart, and fully ready to support humanity's next giant leap into the cosmos. This is how we'll stay connected to each other and to Earth, no matter how far we venture into the depths of space. The interplanetary internet is not just a dream, it's rapidly becoming a reality. Let's see where this incredible technology leads us as we explore the universe. Now, let's see how these breakthroughs power the next wave of missions. Artemis will put humans back on the Moon for good, with a base at the lunar South Pole and the Gateway Station in orbit. Supporting this means massive data HD video, science, astronaut health, and personal calls. LunaNet, a network of satellites using lasers and radio, will keep astronauts connected, even on the Moon's far side. Mars Sample Return will rely on laser comms to coordinate a complex, multi-spacecraft relay and send back high-fidelity video of the process. Europa Clipper, exploring Jupiter's icy moon, will use optical comms to send terabytes of data from 5 times farther than Earth's orbit. The Gateway will be a hub, routing high-bandwidth data from the Moon and Mars back to Earth. These missions are only possible with lasers and DTN. The age of data-rich, interconnected exploration is here. The future is multi-planetary, and it's powered by light. Let's get ready. Radio won't disappear overnight, but its days as the main workhorse are ending. Lasers, quantum comms, and the interplanetary internet are the new foundation for space exploration. Soon, we'll support moon bases, stream 4K from Mars, and unlock the secrets of distant worlds, all thanks to beams of light. It's a fundamental shift in how we explore. The future is bright. Literally. Thanks for watching. Let me know what you want to see next.